Bam! Mr. True. In this video, we're going to continue our look at how derivatives can help us graph functions. Polynomial functions, rational functions, irrational functions. Ultimately, we're going to, we just got done looking at the first derivative, which allows us to find out where functions are increasing and decreasing, which allowed us to then identify where the relative max and mins were in a function and actually find out what those were, as opposed to in pre-calculus where we just kind of had to guesstimate what those values were, or use a calculator to tell us what the relative max and mins were. We're going to be looking at the second derivative test. With the second derivative, we're going to be able to talk about concavity. We're going to be able to talk about inflection points. We're going to use that second derivative test if we have the second derivative available to help us identify relative max and mins, just like the first derivative test does for us, but I actually prefer the first derivative test if I have that available. So let's talk about concavity right now. Let f be differentiable on an open interval I. The graph f is concave up on that interval if the derivative of f is increasing on the interval, and concave down if the derivative of f is decreasing on the interval. So concave up, concave down. If you look at this graph, there's a portion of this graph that if I could pour water on it, it would hold water, assuming it was three-dimensional, and it's kind of, it's curving up, right? Well, this function, we look at it and the first derivative is going to be actually not equal to 0, but negative, because the graph is falling. We have the first derivative here, which is going to be equal to 0. So in other words, the graph has a negative slope. The graph has a a slope equal to 0. And then over here, we have a graph whose first derivative, or slope, is positive. And the graph continues to, increase, right? But you can see that it starts to, the rate at which the slope is increasing starts to slow, and then it would start to fall again, right? And set up, instead of a relative min, somewhere else a relative max possibly. Well, where that rate of increase on the slope, or the first derivative, stops increasing and that starts to decrease at that point of inflection, then we're going to end up somewhere else where the function maybe is like this diagram, concave down. So concave up and then concave down. You can see here as well, I basically have the first derivative test up here. We have a point, a critical value, where the first derivative is equal to 0. To the left, the first derivative is negative. To the right, it's positive. So that would be a relative min. We'll be talking later about how the second derivative helps us to identify this as well. And to the left of this critical value, where the first derivative is equal to 0, we have a positive derivative and a negative derivative, or a positive slope and negative slope, setting up a relative maximum. Okay, so test for concavity. Let f be a function whose second derivative exists on an open interval. If your second derivative is positive for all x in that I, then the graph of f is going to be concave up. If the second derivative is negative, or that's going to be the same thing, except that's going to be indicating that the function is concave down. So in other words, in this graph right here, I have, just some curve representing a function, and I've actually only identified the values or the sign of the values for the first derivative. But if I went another step further and took the derivative of the first derivative and found the second derivative, then within this interval, my second derivative would be positive. And if I took again look at that second derivative, or take the derivative of my first derivative, then in this interval, my second derivative value will be negative. Now, we're going to look at some graphs on the next page and just help us visualize what this first and second derivative is telling us. Where might we find relative max and mins, or even relative max and mins where the first derivative is undefined. Alrighty, what we have on this screen is what I forgot to mention on the bottom right-hand corner of my chalkboard, which is how do we set up the intervals to test for concavity? Well, you need to find that second derivative, of course. You're going to then basically do the same thing that you did when you did the first derivative test. You're going to find out where the second derivative is equal to 0, where it's undefined, and like you can see in my first example here, where is the function, the original function, undefined, or where are there discontinuities? Because to the left, within each of those intervals, you might have the function be, concave up or concave down. So find the second derivative, find out where it's equal to 0 or undefined, and find out where that function, the original function, is undefined. Now, if the function, the original function is undefined at some value, like this first example is undefined at values of pi and 3 pi, well then of course the first and second derivatives are going to be undefined as well. So why worry about where the original function is undefined? Well, when you have the concavity change, you might have, let's say like this example, now these are all kind of special case examples, and well actually we have concavity both up and down here at the same time, but we're going to be talking about inflection points and relative max and mins. And actually that's what I was thinking of. This function here goes from concave up to concave down and back to concave up. You wouldn't want to try and identify an inflection point where the function is undefined. And a function can be continuous where the first and or second derivative is undefined. So you do need to check all three things. So here we have, well, what kind of function do I have graphed up here, by the way? How much do you remember your trig? I've got sort of like a shadow graph here starting at 1, going through pi, dipping to a minimum value at 2 pi, going to 3 pi, and then finally 4 pi. So I've graphed as a guide a cosine with a period of 4 pi, and then went in the opposite directions, or like to kind of blew the graph inside out. Well, if this is a cosine function, then I must have up here the graph of secant. So we have a secant graph up here of a period of 4 pi, and it continues, of course, forever, but we're going to look at this interval between 0 and 4 pi. We have a relative min, a relative max, and a relative min again. We have intervals where the function is concave up, concave down, and then finally again concave up, and of course this will repeat forever if I let the domain go off to negative and positive infinity. And see, what's happening is I've got a place where the second derivative is undefined at pi and at 3 pi, and to the left of that value, or the interval between 0 and pi, I have a graph that's concave up. I have between pi and 3 pi a graph which is concave down, and then back to concave up. So I have identified some areas of concavity that are different, but I don't have an inflection point because at pi and at 3 pi the graph is not continuous. So there is no inflection point, and so again you need to find out where that original function is undefined. Okay, and just again highlighting here, your second derivative will be positive, negative, and positive, indicating that concavity being up, down, or back up. Okay, so again, no inflection points. Here we have a function that has a vertical tangent line, which means that both really the first derivative and second derivative are going to be undefined, and that's a critical value. Again, you need to find out where the second derivative is 0, undefined, and where the original function is undefined or has a discontinuity to set up your intervals. So we have a second derivative which is undefined, a second derivative which is equal to 0, and again that would set up my number line into some intervals, and I'll test just one number. I only need to do one number, and each of these intervals, plugging them into the second derivative and seeing if the sign is positive, negative, or positive. Now this one I've drawn is smooth and continuous everywhere, so we have inflection points at c sub 1, f of c sub 1. So when I find that interval where the concavity goes from being positive to negative, then I'm going to want to take that value of c and plug it back into the original function to identify the inflection points that I'm sure you're going to be needing to find and tell your teacher, just like my students are going to need to do. Okay, so also what I want to mention here is just because you find a critical value doesn't necessarily mean, like we learned in the first derivative test, that you're going to find a relative max or min. This graph actually takes a couple of breaks. It's got a place where there's a vertical tangent line, a place where there's a horizontal tangent line, but it just keeps climbing again, and that first derivative never changes from being positive. So this graph would not have a relative max or min, even though we ended up finding a couple of critical values. Here we have a sharp bend, which means, and it's continuous, so we're looking at a function here that's not smooth, but continuous everywhere. But the first and actually second derivative is going to be undefined at, some value of c. And maybe I should have written that up here. So there's some value of c where the function has a second derivative which is undefined, so it's a critical value. And we test maybe the left and right areas to the left of right of C, we find that our second derivative is positive on both. We can also see here that we have a slope which is positive, so our first derivative is going to be positive. Our first derivative on the right-hand side is going to be negative. So we have a relative max value that we could identify with the first derivative test, testing to the left and right of that critical value to see if we indeed have a relative max or min, and if we go from positive to negative, we have a relative max. So that's at least an idea with a few examples here of some special cases where you're going to be looking for how the concavity changes. Let's take a look at a smooth curve and identify what could possibly the first derivative and then second derivative look like given that original function before we get on to some more notes and finally those three examples. Bye! So here we have a function that appears to be a cubic function or third degree where there's two bends here. So I want to lay over this what could potentially be a first and second derivative function and then fill in some information at the end for your notes. So seems to be that the function is bottoming out here, and so we know that the first derivative at that point is going to be 0. It's a critical value. So I'm going to come down here and highlight that. We're going to make sure that we can hit that point on the x-axis is something that's quite important. We have another place over here where the first derivative appears to be 0. So we're going to drop that down as a critical value. And then, since we're talking about inflection point, even though I haven't really defined it completely for you yet, the graph is falling and it kind of like looks like if I just kept going it would sort of swing around like that. And then there's a place where the graph is sort of cupped down, if you will, or, well, concave down. So somewhere in the middle there's an inflection point where the graph, the rate of change for the slope starts to, it's increasing, 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 and then the rate of change, the slope starts to decrease, the rate of change of the slope. So somewhere in here is the inflection point. We're going to highlight that right here. And let's get the first derivative up here. Now don't forget the first derivative, of course, describes the slope of the original function. And along here, my slope is negative. So my first derivative needs to be giving me values which are negative, or in other words, the first derivative needs to be below the x-axis. Until at least we get to here where the first derivative is equal to 0. So, actually, let's pick a different color. Maybe it looks something like that. Now, the graph goes from being 0, and the slope is increasing and getting greater and greater until, well, actually at the inflection point, it seems like the slope is as steep as it's going to be before it starts to fall again. So, as I draw my first derivative, that needs to be where the highest value of my derivative, roughly is, because it's only a sketch. And it's a guesstimate here, but maybe looks something like this. And then starts to fall. Until at this point, where the slope again stops being positive, goes to 0, and then starts to fall. Well, from here on, the slope is negative, so my first derivative needs to be below the x-axis. Woo! Oh, so pretty! Alright, so that's f prime, or the first derivative of f. And looks like my highest point isn't really my inflection point. Let me just cheat and move that over a little bit. Okay. Yeah, I'm sure that was so important to move that like a half an inch, right? Well, now, this is my first derivative. Now, well, okay, now let's talk about graphing the second derivative. And by the way, this kind of looks like a parabola, right? We have a function that appears to be a third degree, and now I've got a function that looks like it's a second degree, and that should be normal, right? Because when you find the derivative of, say, y equals, well, x cubed, it becomes y equals 3x squared. So it seems normal and actually very correct that this first derivative looks like a parabola. Now let's put the second derivative up here. Now the second derivative is the slope of the first derivative. It just keeps going in steps. And from here up until where my first derivative ends up sort of maxing out, actually I could just say that this is the original function, right? My function has a positive slope, or my derivative has a positive slope until it gets to this critical value, and then it starts to fall. So if I want to draw the second derivative, which is the slope of the first derivative, it had better be above the x-axis where the first derivative has got a positive slope. So we're going to put that dot right there on this critical value where the first derivative goes from being positive to stops rising and starts to fall. And let's draw this line right here. Hit that value, that critical value, which ends up actually being the inflection point. So that definition is coming up very, very soon. And that purple line is the sketch or an approximation of what our second derivative is going to look like. So again, our original function is falling until we get to this point. So the first derivative slope represents that falling or that negative slope. We bottom out, we get a slope that is positive. So my first derivative is above the x-axis where my original function is rising. And then it starts to fall, so that first derivative starts to fall. Now getting into the second derivative, the first derivative has a positive slope until we get to here. So the second derivative is above the x-axis, and then the first derivative starts to fall with a negative slope, and thus the second derivative is below the x-axis. So what we see here is where the second derivative is equal to 0 is a place where you will possibly find an inflection point. Or actually, you will find an inflection point, but those inflection points can happen where the second derivative is equal to 0 or where it's undefined. Now again, if the second derivative is undefined, you need to make sure that your original function is not discontinuous at that point. I'm going to pause the video and write some notes up on this diagram now that we have it drawn so you can include them in your notes. Alright, just filled in some notes, and I'm not going to talk about this too much because obviously I just did, and it's a repetition of a lot of what I've already pointed out. Other than, here we have the inflection point. I'm going to give you a formal definition of that and on the next screen before we get to the examples. And these orange dots, the relative min and the relative max, this is a preview or a visual representation of your second derivative test, which will also be on the next screen. If your first derivative exists and is equal to 0 and the second derivative is positive, then at that point of whatever, c sub 1, f of c sub 1, you have a relative min. And if the first derivative is equal to 0 and the second derivative is negative, at that, of course, same point, then you are doing, or finding, a relative maximum. Honestly, again, there's less work. If you start from an original function, there's less work to get to the first derivative, obviously, than the second derivative. And you'll see on the next screen when we talk about the second derivative test, it's not always able to tell you if a point is a relative min or max. So honestly, kind of really prefer the first derivative test for identifying those relative maxes and mins. But the second derivative test is still something we have to be aware of and, occasionally use, depending on how they give us the information in the problem. Definition of point of inflection. Let f be a function that is continuous on an open interval, and let c be a point in that interval. If the graph of f has a tangent line at this point, c f of c, then this point is a point of inflection of the graph if the concavity of the function changes from either being positive or concave up to concave down, or concave down to concave up. So basically, the concavity changes on each side of this value of c, or to the left and right of c f of c. What this is highlighted here is my book puts this in the definition of a point of inflection. Some books apparently don't. And what that means is that my book would only look at this point as a point of inflection, where at this point c f of c, to the left I'm concave up, to the right I'm concave down. And this would just highlight as a relative minimum. But some books would say this function is continuous here, it is concave down to the left, concave up to the right, thus this is also a point of inflection at that sharp bend. Remember, you can't find you don't have a tangent line at a sharp bend. So this point would fail my particular book's definition of point of inflection. Now, of course, if the function is undefined, then that's still one of the test point intervals. Remember that where the function has got a discontinuity, or where the second derivative is undefined, to the left and to the right we have a change of concavity, but you can't have an inflection point if there's no point. And by the way, the second derivative would be undefined at a sharp bend as well. It's just my book's not going to call that a point of inflection. Some books will. Okay, points of inflection occur where f the second derivative is equal to 0, or where the second derivative is undefined. Remember that first screen with the three pictures, we had that vertical tangent line, and we had a point of inflection there. We went from being concave up to concave down. Second derivative test, if or let f be a function such that f of c, or excuse me, the first derivative of f, or f prime of c, is equal to 0. So our first derivative is equal to 0, or the slope is 0 of our original function. And f double prime exists on an open interval containing c. Well, again, we're only talking about where the first derivative is equal to 0. If f double prime of c is greater than 0, then f has a relative minimum at c, f of c. If your second derivative is greater than 0, then you're concave up, and of course, at the bottom of that concaveness, or the bottom of that curve, you're going to have a relative minimum. If the second derivative is negative, or that means your function is concave down, then at c, f of c, you have a relative maximum. Again, we're talking about only the points where f prime of c, the first derivative, is equal to 0. Now, it is possible in doing the second derivative test that you find a place where your first derivative is equal to 0, but when you go to find f double prime of c, it comes out to be 0, which means basically you've run a test, but you haven't come to a conclusion. Thus, you'll have to fall back on the first derivative test. So if you were given me an actual original function and just said find the relative maxes and mins, I would just find the first derivative and do the first derivative test. But because sometimes the second derivative test fails. Woo! That's a lot of notes. Let's get to some examples. Woo! Man! Tried to look at all these notes. My hand's hurting. First example. Determine the open intervals on which the graph is concave upward or downward. Find the inflection points and any relative max or mins. We're going to find those relative max or mins by looking for critical values of the first derivative, but I want to first talk about concavity, which means I need the second derivative. So if this is our polynomial y, and by the way, polynomials have a domain of all real numbers, so we don't have any issues with the original function being undefined or having discontinuities. So our domain's all real numbers, and y prime, the first derivative, is 2/3 times 3 is equal to 2x squared. 2 times 2 is 4x, and then minus 6. We're going to be using that again to find those relative max and mins in a second. But I'm going to find the second derivative, and that means just repeat the process. We have 2 times 2 is 4x plus 4. Okay, now remember those inflection points and the changes of concavity occur where the second derivative is equal to 0 or undefined, or that original function has a discontinuity. We already know that does not, so we're going to take a look at the second derivative, and we're going to look for where y double prime of x is equal to 0. So we have 4x plus 4 is equal to 0. We're going to subtract both sides by 4. Divide by 4 and get x is equal to 1. Negative 1. Well, I also need to find out where the second derivative is undefined. And where the second derivative is equal to undefined, well, that has no solution. So the only critical values I need to use to set up my intervals to check for concavity is the x value of negative 1. So my intervals are, my test intervals, are going to go from negative infinity to negative 1, and then from negative 1 to positive infinity. And my second derivative in those intervals, I'm going to take one value from this interval, plug it back into the second derivative, and determine if it's positive or negative. So I want to see, let's say, y double prime of negative 2. Okay, well, 4 times negative 2 is negative 8. Negative 8 plus 4 is negative 4. So my second derivative in this interval is negative, which means it's going to be concave down. And on my interval from negative 1 to infinity, I want to test one point in there, like 0. So y double prime well, 4 times 0 is 0. 0 plus 4 is 4. And so, it's nice to know it's 4, but really all I care about is whether that is positive or negative. And since my second derivative is positive, then I have a concave up situation on that interval of negative 1 to infinity. Now, at the value of negative 1, my function, which I know is defined, at negative 1, because it's defined everywhere, at that value of negative 1, my function goes from being concave down to concave up. That means I have an inflection point. So my inflection point is going to be negative 1, comma, f of negative 1, or negative 1. Now I'm going to, right off the top of my head, take negative 1 and plug it into this original function and find that the y value is 8 1/3. And I'm out of space, so let me clean this up a little bit and I'll highlight or write down what information we found so far where the function's concave up and down and that point of inflection and continue this problem. Relative max or mins. Well, we've already studied the first derivative test and learned all about that first derivative, so we're going to take that first derivative, we're going to set it equal to 0, so find out where it's equal to 0. So we got 2x squared plus 4x minus 6 is equal to 0. We're going to factor out a 2, or actually we could just divide both sides by 2 and get x squared plus 2x minus 3 is equal to 0. That is a quadratic. Of course, we can solve it by factoring, we can solve it by completing the square, we can solve it by the quadratic formula, but I knew I was going to have to do this in an example in the video and right in front of you off the top of my head, so it's pretty easily factorable. So this is going to be x plus 3 and x minus 1 is equal to 0. So our first set of critical values we have here is x is equal to negative 3 and 1. Our other critical values would be for where the first derivative is equal to undefined. And that, we have no solution. So we just need to check for relative mins and max at the x values of negative 3 and 1. Now, how are we going to do that? Well, I could do the first derivative test and, plug in a value to the left of negative 3 and to the right of negative 3 and to the left of 1 and the right of 1, but I'm supposed to be teaching you the second derivative test, not the first derivative test. So I'm going to take that value of negative 3 and I'm going to decide, is it a relative min or is it a relative max? I can plug it into the second derivative, which is 4x plus 4, but negative 3 is in this interval. And within the interval of negative infinity to negative 1, well, the original function is concave down. So if the function is concave down and somewhere in that interval, negative 3, the first derivative is equal to 0, then I kind of already have done the second derivative test. Where the first derivative is equal to 0, my second derivative is, well, let's see, concave down, right? So that second derivative was negative. So we have a relative maximum at negative 3, comma, f of negative 3. And again, right off the top of my head, that comes out to be negative 3, 19. Now remember, I'm plugging that negative 3 back into the original function. Okay, my other critical value is at 1. Well, again, the second derivative test says where the first derivative is equal to 0. If the second derivative is positive, then we have a relative minimum. If the second derivative is negative, so it's concave down, we have a relative maximum. Well, at 1, that is in this interval where the function is concave up. So my first derivative is 0, my second derivative is positive. So I'm going to take this value and say, okay, well, my relative min is equal to 1, f of 1, which turns out to be 1, comma, take that 1, plug it back into here. Right off the top of my head, we have a relative minimum at 1, negative 2 1/3. Okay, on to the next example. It's going to be, obviously, I want to go harder as we get through our examples. So this was a basic polynomial. Our next function is going to involve finding the derivative using the product rule and deal with some square roots. Second example, f of x is equal to x times the square root of x plus 6. So we're going to rewrite that as f of x is equal to x times x plus 6 to the 1/2 power. Walk through the product rule. F prime of x is going to be x times, now walking through your chain rule, we got 1/2 times x plus 6 to the negative 1/2, and if you want to just make sure you're practicing the chain rule, times the inside, which is going to be simply equal to 1, which of course means that's really not necessary unless you're just making sure you're reinforcing your skills of the chain rule, plus, okay, so that was the first times the derivative of the second factor, plus the second factor, which is going to be x plus 6 times, or raised up to the 1/2 power, times the derivative of the first factor, which is going to be equal to 1. Okay, so usually when you have radicals, or especially you're working with the quotient rule, there's going to be a little bit of factoring going on. Both of these terms have a factor of x plus 6. You're going to take out the lowest power, which is the negative 1/2. And I like to, when I have a coefficient which is a fraction, because there's going to be some stuff floating, as you can see with the negative exponent, to the denominator, to take that fraction out as well. So I'm going to factor out a 1/2 and the x plus 6 to the negative 1/2 power out of both of these terms, and 1/2 divided by 1/2 is 1. Anything divided by itself, again with that x plus 6 to the negative 1/2, is going to be equal to 1, so we're just left with x plus, and then when you divide like bases, of course, you subtract the exponents, and I'm forgetting that I'm dividing by that 1/2, so 1 divided by 1/2 is 2, times x plus 6 to the 1/2 divided by x plus 6 to the negative 1/2. When you divide like bases, you're supposed to subtract the exponents. Well, 1/2 minus the negative 1/2 is 1/2 plus 1/2, which is 1, so we end up with x plus 6 to the first. Now we're going to distribute this 2 through, and we're going to show all of our steps as we do these problems, because they're very meticulous, and if you make a small mistake, you can carry it through very easily and not notice it till you're done and you check your answer. The more work you show, the easier it is going to be to find your mistake and then fix it. So this 2 is already in the denominator, that 1/2 that we factored out, and the x plus 6 has that negative 1/2 power. So we're going to write the first derivative of f, or f prime of x, is equal to, alright, so we got x plus 2x, just showing all the steps, times 6, which is 12. On the bottom we have 2 times, well, I would write the square root of x plus 6 if I knew I was done, but I want to take one more step and find the second derivative for the concavity and the inflection point, so I'm going to leave it as x plus 6 to the 1/2 power in the denominator. And of course we add like terms, and we get the first derivative is 3 plus x, or 3 times x, plus 12, over 2 times x plus 6 to the 1/2 power. Now I have to go through another derivative process, but this time using the quotient rule. And it's going to be a lot of steps, and I don't want to talk and write something and not catch it in the video, so I'm going to actually pause it and just sort of reveal the answer. And it'd be a good time for you to make sure that, well, if you're really good with your derivatives, maybe you could just see the answer. If you sometimes make some small mistakes, or just want to challenge yourself just for a second to review your quotient rule for finding derivatives, give it a shot. Pause the video. Okay, so we've got, well, just the quotient rule. I have the, what did we have here? The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Just showing every single step, and doing the times 1 again because I'm just showing the continuation of the chain rule till I'm done, even though I'm just multiplying by 1. Might not show that in my own work. These again both have a common factor of x plus 6. You take out that lowest exponent. And what else did I want to show you? Oh, when I bring this x plus 6 to the negative 1/2 down to the denominator, where the 3/2 came from was, again, I'm bringing this down. When I bring it down, it's going to be x plus 6 to the 1/2 power. And when you multiply like bases, you add the exponent. So 1 plus 1/2, of course, is 3/2. And, well, now we have our second and our first derivative. And I'm out of space, so Let me clean this up, put them over here. We'll find those critical values for the second derivative and find the intervals for concavity, the inflection point, go back to the first derivative and, we're only doing second derivative test, and find that those relative max and mins with the second derivative test after we find out where the first derivative is equal to 0. It was a dark and stormy night when I was learning about the second derivative test. I don't know if you're going to hear the thundering, but it just started downpouring as I do this video. Alright, so I want to test for concavity, so I need to find the critical values for the second derivative. Now, I kind of have a bad habit of this where I just start on the problems and I keep forgetting to check the domain of the original function. We cannot square root a number, or even root, excuse me. It's true for square root though too. We can't even root a number which is negative. So before we try and find our critical values and identify where the function is concave up and concave down and where the inflection points are, don't do any work with the functions undefined, right? So this function's domain, I talked about that earlier in the video. The function's domain is, x plus 6 has to remain greater than or equal to 0. So our domain is x is greater than or equal to negative 6. So any values that we find, the critical values outside that domain, is not going to be usable. And I could write that from negative 6 to infinity, of course. So, okay, so for our second derivative, our intervals of interest, we need to find out, well, we're not going to set up our intervals if we don't know our critical values. So that's going to be where is the second derivative equal to 0? So where is f prime equal to, or double prime equal to 0? Well, for a rational function equals 0, the numerator has to be 0. So we got 3x plus 24 is equal to 0. That's 3x is equal to negative 24, and x is equal to negative 8. So that, should be one of our critical values, but negative 8 is not within our domain, so that is not a usable number. Our second derivative, well, where is it equal to being undefined? The original function, other than just domain of negative 6 to infinity, doesn't have any other issues with domain, but now our second derivative has a variable in the denominator. So what's going to make that variable undefined? Well, that is going to be where x plus 6 is equal to 0, and x therefore is equal to negative 6. That's where our second derivative is undefined, and that's just at the very edge, as I stand in front of it, of our domain. Our domain actually starts at negative 6 and goes to the right. So we only have one variable of interest as far as checking concavity, and that is from negative 6 to infinity. So I can put that here. So our intervals that we care about for the second derivative is from negative 6 to infinity. And if I want to find out where the function, if the function is concave up or concave down at that point, I need to take just one value within this interval, like let's pick the easiest one, and do a test value of 0. Well, the second derivative in this interval, if I take 0 and I plug it into my second derivative, I get 3 times 0 is 0 plus 24, so the top is positive. And on the bottom I've got 0 plus 6, which is positive, and so I have a positive number on top and a positive number in the denominator, so my second derivative from negative 6 to infinity is positive. And if my function has got a positive second derivative, then that means that we're concave up. Okay, so we need to define concavity, we need to define inflection points. We only had one test interval, so there's no place for the function to change from being concave up to concave down, so we have no inflection point. And therefore, the only thing left is to identify any relative max or mins. Alright, so let's see, let me get out of the way and clean this board up. I keep writing so big. And we'll come back with that first derivative and find the relative max or min. Okay, to help us finish up the last piece of this puzzle, which is where are those relative max and mins, I went ahead and kind of cheated a little bit because you could very well be doing these problems without the aid of a calculator in some schools. But I drew us this function just to remind us for a couple of things here. One, we can see the concave up that we found between negative 6 and infinity. Secondly, we're going to find a relative min in here somewhere, and it should be obvious because we only have a concave up situation. But I also wanted to just highlight with this particular question that it is defined at -6. I can take -6, remember that's where our domain started, and I can take that -6 and plug it in. -6 plus 6 is 0. The square root of 0 is 0, and thus the answer is 0. So we do have a relative max here at the beginning of the function, because that's a closed dot. It's not an open dot. If it was open at -6, we wouldn't be able to find a relative maximum there. Okay, so relative mins and max occur where the first derivative is equal to, well, has a critical value, whether it's equal to 0 or being undefined. So let's find those values. F prime, where is that equal to 0? Well, it's again a rational function, so let's just set the numerator equal to 0. We got 3x plus 12 is equal to 0. That's 3x is equal to -12. Divide by 3. And x is equal to -4. Okay, well, again, at the x value of -4, the first derivative is equal to 0, and the second derivative, if I come back here to my interval, where I just determined that the function was concave up because my second derivative was positive, if where your first derivative is equal to 0, your second derivative is positive, you have a relative minimum. So the relative minimum is at 4f of 4, which is 4, coming back to my original function, 4 plus 6 is 10, the square root of 10, I'm just going to leave it like that, with a 4 out front. So it's, well, excuse me, don't forget those negatives. -4 square root of 10. Oh, well, that's going to change that answer, isn't it? Let's try that again. -4 plus 6 is 2. And we have -4 square root of 2. Alright, just make sure. Excellent. Okay, now, what's going on here at this beginning part of the function? Well, our first derivative is going to be undefined. Just like our second derivative, it has the same x plus 6 in the denominator. And if you plug in -6, that's going to be undefined. So again, anytime you want to find out where your rational functions are undefined, look to see where the denominator is equal to 0. So we have 2 square roots of x plus 6 is equal to 0. Or you might have noticed, like this previous one, I just focused on the expression that was inside the radical, if you will, or that's going to make the denominator equal to 0, because we're going to divide both sides by 2, which is going to be 0 divided by 2 is 0. Then we're going to have to square both sides, but when you square 0, you still get 0. So I could still just focus on that x plus 6, that algebraic expression with the variable in the denominator that's going to possibly make it equal to 0, and that is x is equal to -6. So yeah, we would have noticed the -4 and the -6. We would have identified both of those as critical values because it just happened to be the function was undefined at -6, or not the function, the first derivative. So we're going to take that -6, plug it back into the original function. So we have a relative max at -6, comma, well, 0. Okay, I got one more example. It's going to be quite a long one. It's going to involve a trig function. And I think, oh, I said I was going to do all 3 examples in this video, but I might actually even do a separate video as well as this one just for the last example. We're going to have y is equal to secant of x over 2 as our next example. Bam! Last example. Now, like before, I'm going to walk out. We're going to find that first and especially second derivative, so we can talk about concavity and the inflection points. We're also going to be highlighting the domain of this original function after I reveal the derivatives to you. If you want to pause the video and practice your derivative skills with your trig functions, make sure you remember, and my students will hopefully have remembered these already, memorize them. The derivative of secant of x is equal to secant x tangent of x, and the derivative of tangent of x is equal to secant squared. Now I'll reveal this in small steps in case you get stuck. You can kind of see, oh, that's the next line, and just keep going, or you can just watch the answers get revealed. I just wanted to start off by finding the domain. So I wrote secant in terms of cosine just to make sure you realize that when the denominator is equal to 0, the function of course is undefined. And cosine of x over 2, if you set that equal to 0 and solve it, then you're going to, you might look at this half angle and go, well, I remember when I worked with multi-angles and pre-calculus or trigonometry that the half angle told me how many times I had to go around the unit circle, and if it was a half angle, I only had to go around the unit circle halfway. But that's because the answers they were looking for were between 0 and 2 pi, and this restricted domain for this problem is 0 to 4 pi. So I actually have to go around the circle basically twice as far as I would normally. Just keep going through until, okay, inverse cosine of 0, that's going to be where you're at pi over 2 or 90 degrees, and 3 pi over 2, and maybe you might carry over and let's see here, let's see, 1, 2, 3, 4, maybe carry it on to 5 pi over 2. But you list off those angles where cosine is equal to 0. You have a half angle, so your last step to solve for x is going to be to multiply both sides by 2. And if you happen to give an extra angle that's beyond this domain, well, then you'll just, forget about it or just not include it. So this function's domain is all real numbers except for where x is equal to pi and 3 pi over, and 3 pi. Hope you got that. We just, of course, use the chain rule. The derivative of secant is secant tangent of the x over 2. And then so I have to, because it's not just a simple x, I have to do the chain rule, the derivative of the inside function of x over 2. The derivative of 1/2 x, or x over 2, is equal to 1/2. Now to find the second derivative, I have two factors being multiplied together. I'm going to let that constant sit with the secant. So I have 1/2 secant x over 2 times tangent x over 2, which means we have to go through the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. So we have 1/2 secant x over 2 times secant squared x over 2 times 1/2, doing the derivative of that inside function of x over 2 again. That 1/2 and 1/2 was what's going to give us the 1/4. And then we have the, the second times the derivative of the first. So I'm, again, just letting the 1/2 sit there, pardon that. I'm just going to let that 1/2 sit out front, so we have the derivative of secant, which is secant x over 2, tangent x over 2, and again, completing that chain rule of the inside function, getting the 1/2. And then 1/2 times 1/2 is again 1/4. To make it easier to find the critical values of the second derivative, I find it easier to put it in terms of sine and cosine. So I wrote secant as 1 over cosine, tangent, of course, is sine over cosine, secant 1 over cosine, and combine all that. So we have the second derivative is equal to 1 plus sine squared x over 2 over 4 cosine cubed of x over 2. So I'm going to erase all this, get the first and second derivative listed over here. And in this rational form, as opposed to leaving secant and tangent, it'll be easier to find out where the second derivative is equal to 0 and where it's undefined, the two conditions we need to check for finding our critical values. Okay, so let's find those critical values to find the intervals at which we're going to test for concavity. So second derivative, where is the second derivative equal to 0? Well, that's I have a rational function again. So the numerator, where's the numerator equal to 0? Well, it's going to be 1 plus sine squared of x over 2 is equal to 0. And at some point you might maybe even immediately realize there's not going to be a solution to this answer because we're going to subtract 1 to both sides and get sine squared x over 2 is equal to -1. And when I go to maybe now you realize you try and square root both sides and you can't square root a negative number. So there's no solution to where the second derivative is equal to 0. So let's turn our attention to where the second derivative is undefined, the denominator. So f double prime is equal to undefined. Well, we're going to set 4 cosine cubed of x over 2 equal to 0. Divide both sides by 4 and get cosine cubed x over 2 is equal to 0. This is starting to look the same as when I checked for the domain. Wonder why? Secant's 1 over cosine, and our denominator is still cosine. So yeah, we're going to get the same answers again. We're going to cube root both sides and get the cosine of x over 2 is equal to 0. And we already know from the previous work, like I said, that our critical values here, when we take the inverse cosine of both sides, well, I was going to just stop, but that was again x over 2 is equal to pi over 2 and 3 pi over 2. Multiply both sides by 2 and we get pi and 3 pi, which means our test intervals that we're going to work with go from negative, I was going to say right negative infinity, but our domain starts at 0. So 0 to pi, and from pi to 3 pi. And of course I'd be including my critical values from where the second derivative was equal to 0, if any existed, from 3 pi to 4 pi. Okay, so we're looking for where the second derivative is equal to either positive or negative for concave up and down. And we're going to have to plug these values into this function. So let's see, do I dare to try and do this on camera? Let's try pi over 2. Pi over 2. Well, if I take pi over 2, because that's between there, divided by 2, I get pi over 4. The sign of pi over 4 is square root of 2 over 2, which is a positive number. It gets squared, and that's a positive number. And 1 plus a positive number is a positive number. And the cosine of x over 2, again, pi over 4 is going to be positive. So this is positive over positive. So my second derivative is positive here. Now if I try, let's see here, between 0 and 3 pi. So let's try 2 pi, should be pretty straightforward. If I try 2 pi, just hesitated because I started working ahead in my head and started thinking I was going to have a sign error. Okay, so we're going to try 2 pi, sorry about that. So 2 pi divided by 2 is pi. The sign of pi is 0. 0 squared is 0, so we have 1 plus 0, so it's positive on the numerator. And then when we take 2 pi and plug it in the denominator, 2 pi divided by 2 is pi. The cosine of pi is negative 1. Negative 1 cubed is still negative 1, times 4 is negative. So we have a positive divided by a negative, so the second derivative here is negative. And then when you plug in, let's see here, how about, yeah, I paused just to make sure I gave you a number between 3 pi and 4 pi. So 7 pi over 2, if you take that and plug it in, you have 7 pi over 4, and the sign of 7 pi over 4, 1, 2, 3, 4, 5, 6, 7 pi over 4 is negative square root of 2 over 2. That squared is going to be positive, and positive plus 1 is going to be a positive answer. In the denominator at 7 pi over 4, your cosine is going to be positive, right? Because in quadrant 4, your x's are positive. And it's going to be, again, 7 pi over 4 is going to be, again, square root of 2 over 2, only this time positive. That cubed is a positive number, times 4 is a positive number. So the second derivative in this last interval of 3 pi to 4 pi is positive. Okay, so it would seem like that I would now have to start talking about, well, I got the concavity of these intervals, up, down, and up. So it would seem like I would start to be checking for inflection points because my function alternates between being concave up and concave up and concave down. But we know that's not what the secant graph looks like. It has a bunch of asymptotes, and we've already checked for our domain, and we know that the function is undefined at pi and 3 pi, which is now where our function is changing for its concavity. So you can't have an inflection point where there's an asymptote. So we have our concavity, we don't have any inflection points, but I need some room to find those relative max and mins. For those relative max and mins, we're going to be looking for where the first derivative is equal to 0. I'm not going to check for it's undefined because I keep having that same denominator of cosine of a half angle, so I know the function is going to be undefined there, no relative max or min. So where's that first derivative? Equal to 0. Well, that means, again, the numerator has to be 0, so we have 1 plus, or excuse me, I'm looking at the second derivative. We have sine of x over 2 is equal to 0. We're going to take the inverse sine of both sides. Sine is equal to 0, well, where y is equal to 0. So we have 0 and pi, and 2 pi. And do I need to keep going? Well, again, our restricted domain is 0 to 4 pi, and if I go beyond 2 pi to 3 pi, I'm going to multiply by 2 to get 6 pi, which is too big. So that's it. We're going to multiply both sides by 2 and get x is equal to 0, 2 pi, and excuse me, 4 pi. Making a lot of crazy little mental mistakes tonight. All right, so those are 3 critical values where the first derivative is equal to 0. Now, the first derivative is equal to 0 here, and in that interval, the second derivative is positive. So this is going to give me a relative min. And at 2 pi, I'm in my interval where my second derivative is negative, so I'm looking at a relative maximum. And then finally at 4 pi, I'm in my last interval where the second derivative is positive, so this is going to be a relative min. So let's list those out. My relative min is going to be 0, and that means I need to take this 0 and plug it into here. Well, let's see. 0 divided by 2 is 0. The secant of 0, well, cosine of 0 is equal to 1. And the reciprocal of 1, because that's secant, is still 1. And at 2 pi, or actually let's do both min values. The other one is at 4 pi. So 4 pi divided by 2 is 2 pi, and if I rotate 2 pi, yeah, right back to where I was in the first place. So that's again going to be equal to 1. And then the relative max, well, that's at 2 pi. So 2 pi divided by 2 is 1 pi, so over here, and the secant is 1 over cosine, so the cosine of pi of pi is negative 1, and if you take negative 1 and you flip it, you're negative 1. So it seems a little bit weird to have minimum values that have higher y values than the relative max, but let's not forget what secant looks like. There's a sort of like it's not a parabola, but sort of like a parabola shape up here, and then it drops down, and so, you know, the relative min and max. When you have sort of a bowl going up, well, then that's a relative min, and when you have another bowl going down, well, then you're going to have a relative max. So that's the end of this example. I'm going to step out and give you a sketch of what this graph looks like, just to tie it all together if you need it. There you go. There's our graph, and before we leave, I just want to make a note. If this was an open interval and not a closed interval, then we would not have been able to identify any relative mins at this point, because we would be approaching that y value of 1, but not actually becoming the y value of 1. So it was closed, so we do have those relative mins and max. Thank you very much for watching. I know this is a long video, but hopefully with these 3 examples, now it's time for you, and you can, go do your homework. Bam! Bam! Mr. Tarrou. And they just scared the birds outside. Bam! Thanks for sticking through all this. We've got a lot more.